Well, first and foremost, I would like to thank Prof. Atina for giving me the opportunity to present my assignment 2. The topic I'm going to present today will be the singular value decomposition for polynomial regression. The idea of this presentation comes from the assignment 2. It's basically the work of the assignment 2. In this slide, I'm going to talk about the description of the problem. In the first point, the polynomial regression to be fitted to data takes in this form. You can see it goes up to the n. N means the data point. Let's say you have the 11 data point, there will be 11. And you can express this polynomial regression in the matrix form. And the problem is to find the value of W1 all the way up to W6, the middle one. In this slide, I'm going to talk about the research methodology. The given linear model can be solved using the singular value decomposition. The earlier matrices is actually the linear model. In order to compute this SVD, it will be computationally expensive. So we are prefer to have the lower computational cost by using the reduced SVD. In the third step, I will be talking about the procedure to compute the full SVD. Basically, there are two steps. The first one is generate the required matrices using the formula given in the assignment 2. Then followed by the computation of full SVD to obtain least square at different conditioning. We are doing t equal to 1 all the way up to 11. There will be 11 conditions. The next thing will be the procedure for the reduced SVD. Similar to the third point, the required matrices need to be generated. Then compute the reduced SVD with K rank approximation from K equal to 1 all the way up to K equal to 6. Lastly, identify the best K rank. In this slide, I'm going to talk about the research methodology. For the full SVD computation, let's say you have the matrix S, 11 times 6. This is the size. We are going to decompose it into 3 other matrices at the different size, and this is called the full SVD. In this slide, I'm going to talk about the reduced SVD. Similar to the earlier one, there will be 3 matrices. The only difference is the different size for the USV. The different size for the 3 matrices is quite convenient to be used because it's more computational efficiency. In this slide, I'm going to talk about the experiment and analysis. I'm going to start with the analysis on the full SVD and rank K approximation. Basically, we are going to generate the matrix S and observation matrix using the MATLAB. Then followed by the decomposition of the matrix S. Decompose it into the full SVD or reduced SVD. Next, we are going to apply the second norm to both full SVD and rank K approximation. Then for the least square, B and B minus SW. That means we will have a generation of the least, but we are going to pick up the best value using the second norm. Then for the full rank, there will be 11 conditions to be solved for the problem with different T. Why 11 conditions? Because we have T equal to 1 all the way up to T equal to 11. Similarly, for the rank K approximation, 6 conditions to be solved at the different K. Because K starting from 1 all the way up to 6, we have 6 conditions. From now on, I will be talking about the experiment on how to proceed all these I will start with the generation of matrix X. This is the code I'm using to create the matrix X. Then followed by the generation of the set of observation B1. Next thing will be the SVD decomposition and find least square for every single t, where t equal to 1 all the way up to 11. That's why you see there are 11 equations here. The next thing will be apply second norm to the least square. Same thing goes to the applying second norm to the approximation B. And lastly, we are going to plot the graph W minus WOPT against B. Of course, we are using the second norm for these two values. From the first slide, the generation of matrix X up to this slide is the problem for the full SVD at the different t value. And now I'm going to talk about the compute rank K approximation. For the generation of the X matrix and also the observation matrix is the same. The only difference is we are going to have the rank K approximation, the code for this part, from K equal to 1 all the way up to K equal to 6. Then we are applying the second norm to the least square at a different K, B minus SW as well. Then we are going to plot X versus capital XW. And right now, I'm going to show you the result and discussion. The result for the singular value decomposition is showing here. As I mentioned just now, we have three matrices, U, X, and V. The most interesting part will be the X. As you can see, they are non-zero value somewhere along the diagonal. We have 4 non-zero diagonal. These 4 non-zero diagonal will be useful for the later analysis, for the discussion part. And in this slide, I'm going to talk about the result for the full SVD as at the varying t. The forward error at varying t, basically we are referring to this part. We want to see what are the effects of the increasing t towards this forward error. As we see, whenever the t is increasing from 1 to 11, this one, the forward error is decreasing. Then, if we look at the B, we will see the same thing. That means whenever the value of t is increasing, both the second norm of B and second norm of forward error is decreasing. And let us move to the next slide. In this slide, I'm going to talk about the plot, the logarithm of the second norm of B versus the logarithm of the second norm of the least square. We will see something like this. It means that whenever the value of one side going down, the other side will go down as well. This is identical to the earlier forward error at the varying t. Then in this slide, I'm going to talk about the discussion for the full SVD. As I mentioned just now, the matrix S is decomposed into 3 components, SUV, and every matrices can be represented as a column vectors. At the increasing value of t, second norm of B is decreasing and second norm of the least square is decreasing too. The goal is to find the smallest value for W minus WOPT by reducing the distance between W and WOPT. The graph is plotted using logarithm form of W minus WOPT and also the norm of B. In this slide, I'm going to talk about the forward error and backward error comparison, different K. Basically, this is the slide for the reduced SVD. And as we can see from here, as the K increasing, then this one, the forward error tend to increase also. Whereas the B minus SW is decreasing. It comes in the different form. One increase, the other one decreasing. And this is how it looks like. In this slide, we are plotting the curve at the different K value and also the curve for the full rank. The dotted one represented the full SVD, whereas the curve represent rank K, different K. It's quite obvious that K equal to 4, equal to 5, equal to 6 are overlapping. The behavior in this slide, I'm going to talk about the discussion for the reduced SVD. The behavior of the second norm of the least square can be seen from the varying value of K. This is actually the forward error. Based on the result, the second norm of the least square is increasing from K equal to 1 to K equal to 6. Similarly, for the backward error, it is decreasing whenever the K increasing. Based on the observation of the different rank from the plot, K equal to 4, 5, 6 are overlapping. From the earlier SVD result, it shows that there are 4 non-singular values. And this indicates the best K is equal to 4. We are likely to have the small K for the computational cost saving. Until now, I present my work. Thank you so much. Thank you, Prof. Athena.